Now we're thinking about current again and current in circuits. Circuit is just some pathway or set of pathways through which current can move, and it allows the current to take a round trip, come back to where it started. That's all it is. Two important fundamentals are called Kirchhoff's laws. There's first of all the junction law. A junction is just a place where several different currents meet. I mean, one or more currents can come into the junction, one or more currents can leave the junction. In this case, there's only a simple case with one current entering the junction, several leaving. Now remember the principle of conservation of current. No matter where you are in the path of a current, the amount of current is the same. So the amount of current right here, for example, has to be the same as the amount of current right here. You can think of this as a point in the path of the current. The only difference is the current is split up into three parts. That doesn't really matter. This is still one point in the path of the current. And the current here has to be the same as the current here. So in other words, in this case, current I1 equals I2 plus I3 plus I4. That's just an example of the more general principle, Kirchhoff's junction law, in which all the current coming into a junction must be equal to all the current coming out of the junction. In this case, all the current coming in was just one current. All the current leaving were three currents. And then there's Kirchhoff's loop law. Imagine that current makes a round trip through a circuit, coming back to the same place where it started. This is both the initial and the final point, moving through the circuit. And in this case, I'm moving through the circuit in a clockwise sense. It doesn't matter which way you go. You could imagine moving through the circuit in a counterclockwise sense. Works just the same thing. So in this circuit, we've got a source of potential difference to get the current flowing, and this potential difference causes there to be an electric field inside the wires, and that causes there to be an electric force on charged particles, and that's what's necessary to push the charged particles through all the resistance that they face in the circuit. Three resistors here, and in this particular case, with this much resistance and this much potential difference, the current will be 1.5 milliamps, 1.5 times 10 to the minus 3 amps. Now, Kirchhoff's loop law says that when you go all the way around, you come back to where you started. If a charged particle were to do that, it would come back to the same place where it started, so it's going to have to come back to the same state in which it started. Right, this point has some value of electric potential. Like every point in this circuit, different points in the circuit will have different values of electrical potential because there are potential differences, because we've inserted a potential difference right here. The potential here is 10 volts, so if a charge starts from this point, at the start it'll have a potential energy equal to its charge times 10 volts. And then when it comes back here, it comes to a point where the potential is 10 volts, and in the end it'll have a final amount of potential energy, which will again be its charge times 10 volts. Comes back to the same state in which it started. In particular, comes back to the same potential where it started, which means that all the changes in potential that it sees in going through the loop have to add up to a net potential change of no change. You get some potential change going from the low to the high potential side of the battery, and you get potential changes going through the resistors. But the net potential change experienced by the particle has to be zero because it comes back to the same potential at which it started. And I'm just writing that out here. The change in potential when you go across the battery, plus the change in potential when you go through the 3 kilogram resistor, plus the change in potential when you go through the 2 kilogram resistor, plus the change when the particle goes through the 1 kilogram resistor. All those changes have to add up to zero. So let's see what those potential changes are specifically and see if they do add up to zero. And to see what those potential changes actually are, we use Ohm's law. Ohm's law tells us that the current flowing through some lump of resistance with this much resistance is pushed through this much resistance by this much potential difference. And specifically, remember, this is the potential difference between the entrance and the exit of that circuit element that has this much resistance. Current is going this way. So here's the entrance, here's the exit. This point has to be at a higher potential than this point. And this potential difference is what is referred to right here. There has to be a potential difference here so that there's an electric field. Electric field points in the direction from higher to lower potential. And then an electric field pointing in this direction means positive charges will feel a force in this direction, and that's the force needed to push them through that lump of resistance, because resistance means that any charged object that passes through that has to deal with a backward force, some kind of drag force. So anyway, we need to use this, or actually we use it in the form resistance times the amount of current passing through that resistance equals the size of the potential change, the potential difference between the two ends of that resistance. So what are the total potential changes here? As you go from here to, remember we're starting here, then we go from here to here. You go from the low potential side to the high potential side of the battery. The potential increases by 9 volts. So if the potential was 10 volts here, now here it's 19 volts. And then we use a model in which all the wires are assumed to be ideal wires with no resistance. And as you've seen before, no resistance means no potential changes. Okay. Current flowing through something with zero resistance, there's going to be zero potential change. And since this is ideal wire and there's no potential change from any point to any other point along that wire, every point in that ideal wire must be at the same potential. No potential change. So the potential is still 19 volts when you get to there. But remember, we're assuming always conventional current. In other words, we're assuming that it's positive charge that's being pushed around. And electric field points in the direction of the force on a positive charge. So positive charge gets pushed this way. So at first, when the positive charge enters this resistance, it sees a higher potential, and then at the end, when it leaves that resistor, it sees a lower potential. It sees a potential decrease, in other words, as it moves through that lump of resistance. So those are all going to be negative potential changes. And let's see how big each one is. Through the 3 kilo ohm resistor, I times R is the potential change, but potential difference between one side and the other of that resistor. And that's just 1.5 times 10 to the minus 3 amps times 3 times 10 to the 3 kilo ohms. That's what the K stands for. 3 kilo ohms, 3,000 ohms. 3 times 10 to the plus 3. And that gives us 4.5 volts. If you multiply amps times ohms, you automatically get volts. If you multiply milliamps times ohms, you don't get volts, you get millivolts. So to have the correct units, you have to write this in amps, not milliamps. So the potential difference between here and here is a drop of 4.5 volts. Which means the potential here, 4.5 volts less than it was here, so the potential here must be 14.5 volts. And because that's ideal wire, it's the same potential all the way through that wire. And then it comes to another potential drop as it moves from the one side to the other side of this resistance. Same as before. This end has to be at a higher potential, this end has to be at a low potential so that there's an electric field pointing from high to low potential that will cause a force that pushes the positive charges through that resistance. And the amount of potential change, it's a potential decrease because this is at a higher and the exit side is at a lower potential. That amount of potential change is, again, use Ohm's law. The potential change is I times R, which is again 1.5 10 to the minus 3 amps times resistance of 2 kilo ohms. 2 times 10 to the 3 ohms, and that gives us 3 volts. A decrease of 3 volts, because you're going from a higher to a lower potential if you move in this direction. So the potential change through the 2 kilo ohm resistor is a drop of 3 volts. So the potential here, 3 volts less than it was here. So here, the potential must be 11.5 volts. 3 volts less than this. And again, since it's ideal wire, every point from here to here, all points from here to here are connected by nothing but ideal wire, so they're all at the same potential. Potential right here at the entrance to the last resistor is also 11.5 volts, and this will be at a somewhat lower potential. How much lower? Use Ohm's law again. change in potential is the current, 1.5 10 to the minus 3 amps, times what? 1 times 10 to the plus 3 ohms, 1,000 ohms. So that's obviously 1.5 volts. So a decrease of 1.5 volts. So this point is 1.5 volts lower than this point. So this point right here is at a potential of 10 volts. And that's exactly what it has to be, because this point and this point, which we already knew was at 10 volts, this point and this point are connected by nothing but ideal wire, so there's no potential change along ideal wire. All points in ideal wire are at the same potential. So this point has to come out to be the same potential as this point, and that's exactly how it turns out. Or to put it another way, the potential increase, when we took this first step of the loop, is subtracted away completely when we go through the potential decreases in the rest of the loop. The potential increase, when you take the first step through the loop, is totally subtracted away when you go through the potential drops, the potential decreases through each resistor. Some of those numbers is just minus 9 volts. So that's an example of how the loop law works. And we'll be looking at plenty of examples of applying the loop law in the next few days. But here's two other things you should think about. In any circuit that's made up of a source of potential difference, like a battery or connection to a wall socket, whatever, if it has a source of potential difference so that current can flow, and then a bunch of resistances through which all that current flows, there's always something we can do no matter how complicated the circuit might look. Just take, say, a source of potential difference, and it pushes some current, delta V volts of potential difference, pushes I amps of current through a complicated mess, a complicated network of a whole bunch of resistances. But here's the trick. It's always possible, no matter how complicated the circuit might look, it's always possible to find a simple circuit that is equivalent to this. It's always possible to find a much, much simpler circuit that is equivalent to this. Equivalent in the sense that the same potential difference pushes the same amount of current into the resistance. So in this simple, imaginary, simple but equivalent circuit, the same delta V volts of potential pushes the same I amps of current through resistance. In this case, this mess of complicated resistance is simply reduced to one imaginary resistor we call it the equivalent resistance because in combination with the same potential difference as before, it gives us the same current as before. This mess of resistors in combination with this potential difference gave us this much current. This one imaginary resistor is equivalent to that mess because it, in the equivalent resistance in combination with the same potential difference, gives us the same current pushed through the resistance. To simplify from a complicated network like this into the simple equivalent circuit, we have a couple of rules. And the rules work like this. Let's say you've got a bunch of resistances, all one after the other in the same path. And there could be any number. Let's say there's n resistors. N could be any positive integer. And they're all different. Now, there is a certain amount of potential difference between this point and this point. Because as we saw a few minutes earlier, every time current moves from the entrance to the exit of one lump of resistance, it experiences a decrease in potential. So there's a decrease in potential from here to here, and then another decrease in potential from here to here, and again, decreases in potential as you go through all the other resistors up to n resistors. So that when you add up all of those decreases in potential, the grand total difference between here and here, the grand total potential difference is just the sum of this potential difference plus this one plus all the other ones. Like that. Okay, now, what else do we know about all those resistances, one after another, all in the same path? They have the same current, because at every point in one path, like for example, in every lump of resistance, you have the same current. Whatever the current is here, it's the same here and the same everywhere else. So I could rewrite this a little bit. The grand total potential difference between the entrance to the first resistor and the exit from the last resistor is the sum of the potential differences across the individual resistances, but now using Ohm's law, we know that this is current times resistance. The same current through all n resistors times the first resistor's resistance. And then the potential difference here is current times resistance. The same current through all of them times the particular resistance of that one, up until you get the nth potential difference, which is current times the resistance in the nth resistor. Well, you can simplify that a little bit by factoring out the common factor, which is I, the same current all the time, everywhere. So remember what we're looking for. We're looking for a simplification. There is a particular kind of simplification here in which this whole series of resistances can be thought of as equivalent to just one imaginary resistor that has the same effect. Same effect meaning you'll get the same current flowing through and have exactly the same potential difference between the two ends. So all this is equivalent to just one imaginary resistance with just the right amount of resistance, but equivalent in the sense that you've got the same current flowing and the same potential change pushing that current. Well, if you just apply Ohm's law to that, that's pretty straightforward. Delta V equals current times that equivalent resistance. This is supposed to be equivalent to the situation where you had N resistors. And when you had N resistors, this is how we wrote delta V equals current times some amount of resistance. But whether we're thinking about the actual real N resistances all in a row or the one imaginary resistor that is equivalent to that series, it's equivalent because it's the same potential difference and the same current. So if these terms are the same and if these factors are the same, then this factor has to be the same as that factor. The value of the equivalent resistance is just the sum of the individual resistors in the real circuit. And that kind of makes sense. If you want a handy label, we call this the equivalent resistance of resistors in series, just one after the other, where series actually means they all share the same current. So that's one way in which you can simplify a circuit by taking a whole bunch of resistances and condensing them down into one imaginary resistor that has exactly the same effect. Here's the other rule. Let's say instead of having a whole bunch of resistances that share the same current, let's imagine a whole bunch of different resistances that share the same potential difference. That is, they're all attached to the same battery or the same wall socket in this kind of way. Again, N resistors now attached so that they have the same potential difference. And we know that they all have the same potential difference, and it's the same potential difference as this battery or wall socket or whatever it is. We know it's all the same potential difference because of the ideal wire approximation. All these points, the high potential side of the battery and the entrances to the resistors, are all connected by nothing but ideal wire. And there is no potential change when you move through ideal wire, so all those points are at exactly the same potential. Whatever the potential is there, it's the same here and here and here and here. And likewise, these points, the low potential pole of the battery and the exit points of all the resistances are all connected by ideal wire, so there's no potential difference between any of those locations. They're all the same potential. Whatever the potential is there, it's exactly the same there and there and there and there. So obviously, whatever the potential difference is between this and this potential, it's exactly the same as the potential difference between here and here, and exactly the same as the potential difference between here and here, and exactly the same as the potential difference between here, and so forth. So what we have here, delta V supplied by our battery or wall socket equals the potential difference between the two ends of resistor 1 plus the potential difference between, and that's equal to the potential difference between the two ends of resistor 2 and equal to the potential difference between the two ends of resistor 3, on and on, etc., equal to the potential difference between the two ends of resistor N. A situation like this where circuit elements have the same potential difference, we call that parallel. Parallel means they have the same potential difference. In other words, and they have the same potential difference because the corresponding sides are connected by nothing but ideal wire. Right? These resistors are in parallel because the corresponding sides, the sides where current enters, are connected by nothing but wire, and these corresponding sides, the sides of the resistor where the current leaves, they're connected by nothing but ideal wire. Okay, now this potential difference pushes a certain amount of current through all this resistance, but we know that's equal to a simple circuit in which the same potential difference pushes the same current through just one resistance, a resistance that's equivalent to all this, equivalent in the sense that when you combine the same potential difference with this equivalent resistance, you get the same current. Now let's see how we can get from here to here. Right, that amount of current is just what you get when this much potential difference has to push current through this much resistance. And it's the same current producing the same potential difference producing the same current, because the effect of all these things is exactly the same as the effect of just this one. So let's see how we can jump from the inventor rule that takes us from the complicated case to the simple case. And to do that, we start by thinking about the junction rule. Just imagine I1 as the current passing through resistor 1, and I2 goes through resistor 2, and current 3 goes through resistor 3, and the nth current goes through resistor N. It may not look like it, but this whole thing right here is a junction. Because what do you have? You've got one current, I, coming in, and then all these currents coming out. And there's nothing connecting this point to this point, to this point, to this point, to this point. There's nothing connecting all those points except ideal wire. Everything is at the same potential. So really, nothing happens between here and all these exit points. Just current coming in at one point and current coming out at end points. So all the current going in has to equal all the current going out. I1 plus I2 plus IN. Well, we can use Ohm's law to rewrite what each of these currents are in terms of the potential difference between the two ends of a resistor and that amount of resistance. So, grand total current is I1, which is potential difference divided by resistance 1. And similarly, current 2 is potential difference divided by resistance 2, etc., etc. And then the nth current is potential difference through the nth resistor divided by the resistance of the nth resistor. And again, just like before, there's a common factor to all n of those terms, and we factor out that common factor, and we then have common factor is delta V. So after we've factored out that common factor, what's left? 1 over R1 plus 1 over R2, etc., until we have 1 over Rn. Okay. The same current is pushed by you get the same current from the same potential difference, whether you have this complicated network of n resistors or you have just one equivalent resistance. So comparing the two, currents are the same, delta V is the same, so the one remaining factor is 1 over R equivalent. And this factor, 1 over R equivalent, has to be the same as the one remaining factor in this equation. The inverse of the equivalent resistance is the sum of the inverses. Like that. And that's the rule for resistances in parallel. Resistances that all share the same potential difference. Let's look at a simple example now where we use these two rules for equivalent resistance in series and equivalent resistance in parallel to take a somewhat complicated circuit and simplify it down into the equivalent simple circuit. So our complicated circuit will look like this. Say a 9-volt battery And then here's one resistor, to keep the numbers relatively simple, 3 ohms. And then here's a 1 ohm resistor, and then a 2 ohm resistor in parallel with that, and then a 3 ohm resistor in parallel with both of those. And we want to find the simple equivalent circuit in which you get the same amount of current pushed by the same 9 volts through just one resistor that has the same effect as these 4. And we simplify in stages. We find a bunch of resistances that are either in series or in parallel and simplify that part. And then repeat the process as many times as we have to. Well, there's 3 that are in parallel. So this circuit is equivalent to a simpler circuit in which the same 9 volts pushes the same current through that 3 ohm resistor and one equivalent resistance that has the same effect as those 3. And what is that equivalent resistance? 1 over that equivalent resistance is the sum of the inverses. 1 over 1 ohm plus 1 over 2 ohms plus 1 over 3 ohms. Okay, you're adding fractions here, and the fractions all have different denominators, so you need a common denominator in order to add. Smallest common denominator is going to be 6 ohms. So this is equal to 6 over 6 ohms. This is equal to 3 over 6 ohms. And this is equal to 2 over 6 ohms. Now add them all up. 6 plus 3, 9, plus 2, that's 11. 11 over 6 ohms. That's 1 over the equivalent resistance. So the equivalent resistance itself is 11 over 6 ohms, just slightly less than 2 ohms. Oh, something was wrong here. Okay. The inverse. The inverse of 11/6 is 6/11. So the equivalent resistance is 6/11 ohms. 6/11 ohms, just slightly more than 1/2. Okay, so now there's one more simplification we need to do to get to the simplest equivalent circuit. And to do that, we know that now we've got 2 resistances in series. So that's equivalent to just one resistor whose resistance is the sum. So that circuit is equal to same voltage pushing the same current through just one equivalent resistance. It's the equivalent resistance equivalent to a couple in series, so it's just a sum, this plus this, or 3 ohms plus 6/11 ohms, And if you want to add them together to get just one rational number, adding two fractions, so you got to have a common denominator, which is going to be 11. So this is the same as 33/11 ohms plus 6/11 ohms. So 39/11 ohms, just a little more than 3 ohms. So there it is. Now, actually, we can figure out a few more things. We can figure out exactly what this current is, because now we can apply Ohm's law to the simple circuit. So Ohm's law applied to the simple circuit, you've got 9 volts pushing some current through 39/11 ohms. So the actual value of that current, just do Ohm's law, the actual value of that current is potential difference 9 volts divided by the resistance, which is 39/11, or you've got a 1/11 in the denominator, so it makes more sense to have that as a times 11 in the numerator. Like that. So that's whatever that turns out to be, something something slightly less than 3. amps. And thinking about any other circuit, you're doing the same things. You're not doing anything that you haven't seen here. The details look a little bit different from one situation to another, but you're always thinking about the same things. Equivalent resistances of a bunch of resistors in series, equivalent resistance for a bunch of resistors in parallel. You'll often need to think carefully about the ideal wire approximation. And that's just about, and then use Kirchhoff's laws, the junction law and the loop law. And then in class we'll see plenty of examples of that.